This is lesson 2 for the factoring of rational expressions unit. And we are going to take a look at polynomials that have this form. So it's 1x squared plus bx plus c, where b and c are some integer. All right, so we really have two steps here. The first thing you want to look for is a GCF. So we want to factor GCF, which is what we learned in the last lesson, if necessary. Okay, sometimes there isn't a GCF. Then, to factor this is a trinomial because there are three terms where the lead coefficient is 1. So it's very specific to this type. You want to find two numbers such that their sum, oh, that looks like one word, let me make that a little neater, sorry, is B, this B right here, and their product is C. Okay, and then I'll show you the notation we use with these two numbers that we have. Okay, so looking at example 1, again, I'm going to start by looking for greatest common factor, and I don't have one. I should actually move this so you can see example 1. So now what I need to do is come up with two numbers that when I add them, I get 11, and when I multiply them, I get 30. So those two numbers are 5 and 6, or 6 and 5. Doesn't matter. The order does not matter. So we're going to set it up like this. The variable is x, and our numbers that we found were positive 5 and positive 6. So we're going to put plus 5 in one of them and plus 6 in the other. Again, the order doesn't matter. Now, if you were to multiply this out, distribute this x, and then distribute this 5, this is what you would get. Let's take a look at example 2. Do I have a greatest common factor? I do not. All right, so I'm going to set this up. Oops. All right, I need two numbers that when I add them, I get negative 11, and when I multiply them, I get positive 24. So you have to be careful of your signs as well. In this case, the two numbers are negative 8 and negative 3. If I add them, I get negative 11. If I multiply them, I get positive 24. Again, the order doesn't matter. If you put minus 3 here and minus 8 there, you're still correct. Example 3. GCF? No. Let's set it up. Now, if you need a little more time to think, you can always pause me. So we need two numbers that when we add them, we get positive 9, and when we multiply them, we get negative 10. Pause me if you need some more time to think about it. And those two numbers are positive 10 and negative 1. Again, if you switch them, this would be negative 1, and that would be positive 10. Totally fine. All right. Example 4. Again, no GCF. And for this one, we need two numbers that add to negative 4 and multiply to negative 21. So 7 and 3 would multiply to 21. So let's see, to add to negative 4, I would need the 7 to be negative. Okay, when I double check, when I add them, it's negative 4. When I multiply them, it's negative 21. Okay, example 5. GCF. Yes. I have a GCF of 5. Okay, so I will divide each of these terms by 5, and that gives me x squared plus 16x plus 63. And now I'm going to factor this trinomial like I've been doing. I'm going to set it up here. I need two numbers that when I add them, I get 16, and when I multiply them, I get 63. So that's positive 7 and 9. Example 6. GCF? Yes. All of those numbers are divisible by 4. Here's a little hint. Usually I look at this first coefficient and see if they're all divisible by it. And in this case they are, and then I check out my variables. This term doesn't have a variable, so there's no variable in the GCF. All right, when I divide all three terms by 4, I get x squared minus 16x plus 60. Now we factor the trinomial. Two numbers that when we add them, we get negative 16, and when we multiply them, we get positive 60, negative 10, and negative 6. Example 7. Do I have a GCF of 2? Yes. And then they each have an x, so the GCF would be 2x squared. So I will divide each of these terms by 2x squared. So when I do, that leaves me with x squared plus 3x minus 18. All right, now I'm going to factor this trinomial. Notice how when we are factoring the trinomials, like in example 5, I said the answers are 7 and 9. You don't just write a 7 and a 9. You have to put this whole thing out there. All right, we need two numbers that when we add them, we get 3, and when we multiply them, we get 18. So those two numbers are positive 6 and negative 3. Again, I think you need a little more wait time, so you have to pause me so you can think about it as well. Example 8, the GCF of 3, yes. Of x, yes, 3x. Divide all three terms by 3x. So when we do, I get x squared here minus 3x, and then here minus 70. And then I'm setting up. Okay. I need two numbers that when I add them, I get negative 3, and when I multiply them, negative 70. So that would be negative 10 and positive 7. All right. That's the first page. So this is trinomial factoring. Okay. Let's go to the next page. We are going to be able to factor the difference of two squares. But before we do, let's talk about what perfect squares are. So when we're talking about numbers, it's numbers where we can take the square root and get an integer answer. So the first few perfect squares are 1, 4, 9, 16. Do you see what's happening here? 1 times 1, 2 times 2, 3 times 3, 4 times 4, 25, 36, 49, 64, 81, 100, and it goes on. Okay, so those are the first 10. If we talk about variables, here are some examples of perfect square variables, like x squared, or a to the 4th, or b to the 10th, or c to the 8th. What we really have here are even exponents. Okay, so now you have to be able to recognize that what a perfect square is. So you might have one of these coefficients and then one of these variables, or just the coefficient, or just the variable, okay? So the difference of two squares, you're going to have something squared minus something. And when I say squared, I mean it's a perfect square. That doesn't mean it has to be to the second power. Like this is really b to the 5th squared. This is really a to the 2nd squared, okay? This is really 5 squared. So then our formula is you take the square root of this first term, you take the square root of the second term, one gets a plus, one gets a minus, and you're done. But it has to be the difference. If there is a plus sign here, it's a no-go. It can't be factored, at least not this way. Okay, let's see what the heck I'm talking about here. Now, because this is on the worksheet, of course these are all perfect squares, but let's just double check. First of all, is there a GCF? No. Is 9 a perfect square? Yes. Is x squared a perfect square? Yeah, it's even one of the ones listed. It has an even exponent. So we can factor this. The square root of 9 is 3. The square root of x squared is x. One of them gets a plus, the other one gets a minus. Done. Again, if you were to multiply all this out, you would get 9 minus x squared. Example 10. Do we have a GCF? We do not. Are these perfect squares? Yes, because the exponent is even, and 16, yes, that's a perfect square. All right. The square root of a to the 6th, we take half of this, a to the 3rd. If you remember your properties of exponents, that'll come a little easier to you. The square root of 16 is 4. One of them gets a plus, one of them gets a minus. Again, it doesn't matter. Like here I put the plus sign in this one, and here I put the plus sign in this one. It does not matter. Example 11, GCF. No. Okay. Are these perfect squares? Yes and yes. The square root of 49b squared is 7b. The square root of 9 is 3. Plus, minus, or minus, plus. Example 12, GCF. No. Perfect squares? Yes. The square root of 25 is 5. Why don't we put our signs in right now? You can wait till the end if you like. The square root of x squared y to the 8th is x y to the 4th. GCF, no. Perfect squares, yes. The square root of 36w to the 10th is 6w to the 5th. The square root of 1 is 1. Example 14. There is no GCF, and this is the difference of two squares. Again, if there's a plus sign here, it's not the difference of two squares. It's the sum of two squares, which we can't factor. All right, so the square root of x squared, the square root of 100, plus, minus. All right. Example 15, GCF. Yes. 2 would be our GCF, so 2, so that leaves me with 4x squared minus 9. Now inside here I see that these are perfect squares, and they are being subtracted. So the square root of 4x squared is 2x. The square root of 9 is 3. Example 16. We do have a GCF. It's 3x. So now we have x squared. We're dividing both of these by 3x. So x squared minus 4y squared. And this is the difference of two perfect squares. Things are getting a little tight here. All right, the square root of x squared. The square root of 4y squared is 2y. Last example, this does have a GCF of 5a. So that leaves us with 9x squared minus 4. And this is the difference of two squares, so 5a The square root of 9x squared is 3x. The square root of 4 is 2. One gets a plus, the other gets a minus. And there we go. Okay, give those practice problems a shot.